Hey, welcome to episode 18 of the 4coder Lexer project. This time we are working on fixing up the flag stuff. So there's a couple of things about the flags that seems weird. I want to add in just a little thing here to help me debug. So what I'm going to do is say, let's print out the flag number here, because I have a little suspicion that the flag number is wrong. So show me the pin flag number. Right, so flag 0, these all appear to be flag 0. So the question is, why would that be the case? We have more than just one flag. Each of these should really be showing interesting numbers, and they're not. So the next question is, are these all the same flag pointer, or do the pointers actually point to different things that just have the wrong flag number? A8, 396388, 396390. So these are different flag pointers, and they just are all showing the same flag because something is bad, right? So, alright, we know that we have different flag pointers coming in. We just, for some reason, don't have different numbers on them. So we should have had different numbers on them because we did flags set numbers. Unless there's something we did that would have change the flag numbers again. I don't think anything here would have caused that. So what I want to do is I want to run through what else could cause that? I do an opt copy model. Hopefully all the flag pointers, I'll bet you the flag pointers don't get fixed up properly, do they? So all my flag pointers are actually pointing to the old model's flags still. Okay, opt copy model. When we go to copy a model, we copy its flags, and I bet we just copy the flags like that. But that doesn't quite work because anywhere that we have a condition that's pointing to a flag, we actually need to remap it into the right flag pointer for this copy of the model. So copy state set, when you go to copy a transition, you just do a copy of the whole condition right here, which is fine, except that that's going to copy all the flag pointers. So what we need to do is have a pass over all of this afterwards that fixes up flag pointers. And the way we can do that, there's one pretty easy way we can do that, which is if we make sure that both models have flag numbers assigned at that time. So copy model, I want to opt flags set numbers on this model, and then after the copy I want to do that on this model as well. So they're both going to have copied numbers. Copied flag numbers, right? And then we can do a flag pointer check fix up, but the problem is that that doesn't quite work because copy state set doesn't know about that. Copy flag set is kind of just a useless function because you can't actually copy a flag set in place. So I guess what's actually happening is that this logic here needs to be inlined, and then it'll make more sense. So the result is not correct. The result needs to be the result.flags now. We make a new flag, and then this is going to be kind of like when we do the okay, so we're getting rid of copy that, take that away. This code here does the state set copy. Copy state set doesn't make a lot of sense either from this perspective. So it's also just going to be moved into being a inline of this. And there we go. And then what we have to do is look at all of the we're going to put that there. Pointer count. There we go. Now you're fine like that. So that'll make those. And then as we're going making new flags, we're going to just stick them into the same thing. So there's the old flag and the new flag, and the new flag to the old flag, right? And then there's, whenever we go to do any of this code that works on result down here, result wants to become result.states now, because we already had result being a state set before, but now it's actually result.states that's the state set. So finally, when we do a condition copy, we need to look at all of the pieces of that condition, and well, first of all, how does condition copy actually help me? Condition copy is just doing a condition set copy, which we already know we want for other reasons anyway, so that isn't actually going to be something we want to change. But what we do want to change is when we do a condition copy, I should pass down the table that takes old to new, like this, so that once you've got the condition set, you can, what is inside of a condition set? Condition nodes. Condition node, take the result.first condition node, and then for each condition node we're going to grab the field set, and then for each field set we're going to iterate the pin list, and for each pin list we're going to iterate the flag pins, or just the pins, and for each pin we're going to set the flag equal to flag putter int as putter val u64 val equals 0 table lookup. We're going to look up into the old to new table. We're going to ask you to find the putter as int that you get when you look at this pin's old flag. We're going to assert that the lookup finds a match, and then we're going to read out of the table that value we just got, and finally we're going to stick that into the pin pointer here. So that'll take the old pin pointer to a new pin pointer. Hopefully that is essentially the problem we are looking at here. There we go. Hey, there we go. That looks better. So now we're getting actual codes in there that look like they may be referred to different things, which is what I was worried about. Very good, very good. Great. Alright, so flag checks look better now. That only took a little bit of our time here at the beginning, and we had to rewrite copy model a little bit so that it would fix up the flag pointers properly. That's good now. So when we come down here to copy model, we set the numbers of the flags and the states, and we are getting correct behavior out from the flag checks. So flag checks, check, done. Next move, we need to look at how to implement input checks. So input checks essentially work with flag checks in the following way. Each node that we're looking at, not here, that's all the end of file stuff. Here, each node we're looking at can have any array of inputs as long as it doesn't include an end of file input, which gets handled in this handler. So anything we see that matches the input we want should be required for this to become true, right? So this is going to be true by itself right now a lot of the time, right? True, true, and it'll be true whenever the flags match, no matter what the input is. So what we want to do is wrap all that in a second conditional check that only lets this code execute if it matches the condition. There will be a couple of exceptions. So first of all, let me take this and say, all right, that's inside that if there. This is all going to be inside of another conditional. And that conditional is going to have the following properties. If the node next does not equal 0, first of all, we're not going to print this conditional if this is the last handler, because the last handler should be allowed to always go so that we have a fallback. But if this is the last handler, then we're going to put in a conditional thing here that only evaluates to true, or only lets code flow into this block if the current input matches something we expect. So how are we going to pull that off? Well, first of all, how do we read the current input? We read the current input by going *putter. We know that that's valid because if this was not valid, it would be already caught in the putter equals OPL putter case, right? This is the one that checks if we're at the end of file. So we aren't getting caught by this. Therefore, it's safe to dereference our pointer. So we're going to switch on the putter there. Then what we're going to do is we're going to say that we have a number of inputs that we have a number of inputs that can trigger this spot. So for each of the inputs in inputs count, fprintf the following thing. Give me a case handler that takes that input value as a trigger for this condition, right? So now if we have just one input, this will print out, switch on the putter, the number that we want to check if it's equal to this thing, and then the if inside that, right? If there are like 100 things, then it'll print out a list of 100 different cases where that putter, if that putter gives that value, that it'll work. Now, this is where we're kind of being sloppy, right, with our output performance, which is not good. We want to actually clean this up a little bit because we don't know that the compiler, especially the debug compiler, is going to do a very good job of tightening this up. Now, a particularly good compiler should actually be able to do a good job of what we're going to do manually, which is looking at the set of values that are being tested against here and optimizing it down to easier to make checks. But I don't necessarily trust compilers to do that in a debug situation, or to have a full, like, we have particular context, we have like information about what types of checks these are. We know things about the checks that the compiler might not realize it can assume. So any attempt we make at adding optimization will probably, at the very least, not pessimize it, and we have some chance of finding things that we can do better if we are a little bit aggressive with assuming things from the context of our scenario and bringing them into how we optimize. But for now, let's see if we get something that looks right. So here we're not doing an input check because the input check is this basically. The putter equals OPL putter is the input check. But here, this is checking all kinds of stuff. What does that look like to me? That looks like, if that's checking to see if it's an identifier, then it's not giving me all the possible inputs that could lead to an identifier. This is certainly a lot of them, but a lot of them are missing too. Anything over 128 is missing, and it should be in there. And so something has happened in the process of creating this system that we've lost that, right? So we have two different handlers here that want to go to so it's not if node next does not equal 0. That's just wrong. So we're going to take that out. So there's everything over 128 showing up. Now, one question I have is why are those in separate nodes? They both have the exact same flags, so I guess I just never wrote the thing that like simplifies unions. But if we simplified unions at the high level, this would work out a little better, and these would all show up together. But you can see already that like we're outputting this, a thing that goes from 128 to 255, and for what reason? Well, because we haven't done anything to compress the idea of ranges. So we just have this thing that's like every possible value that could ever trigger this is listed in a case handler here, and then we do this go to identifier, right? So there's a couple different problems here. One is that we probably want to be able to do things like range compression of these to turn them into a reasonable number of checks. For instance, we know, for instance, that instead of bothering to make the compiler optimize this, we could just say, look, check as a special case that we're looking at 128 through 255, because that's probably a case we'll have a lot, as we're generally parsing ASCII and giving all UTF-8 characters the same behavior. Here we could probably do something similar, like we know that this is going to be the letter ranges, so capital letters, lowercase letters, and underscore, for instance, are all in here, plus I think $. And so we could just make a couple of ranges for those two letter ranges and then poke out the couple of things where we have stuff missing, like you can see here 117 is missing. So instead of having this complicated switch that might just not even optimize and turn into checking this against every single one of these numbers, if we're unlucky, we could instead rewrite this to like basically say if the putter is inside this range but it's not inside but it's not equal to this value or this value or this value, or if it's inside this range and not this value, right? There are ways we could, if we do some crunching on the set here, compress the set, and in the process of compressing the set, find also a way to express the set in a small number of comparisons, and hopefully in that way find a way to determine, if we're doing this test, that the compiler won't be tempted to just turn into a chain of if-else ifs, right? In any scenario ever, even in debug scenarios, right? So yeah, that is what we probably want to look at doing some point in the future, but for now we're going to rely on the compiler to do a good job with that as well as it can, and we have to keep in mind that sometimes the switch might actually be the preferable method. Like this we could easily replace with something that doesn't use a switch, but like something like this might actually be preferable with a switch if it turns out the compiler can do a handy trick, although that's just usually the best tricks come from like more regular patterns. Like if every number between 0 and 100 or something is used and there aren't like gaps like there are here, that's usually a little better for the compiler. I don't know, because then it can look up in a lookup table. This might be a range that's like, it's a little bit awkward to make it into a lookup table directly, like it's got everything from 36 to 120, and so it's just, you know, hard to say what the compiler will do with this without taking a look directly. A lot of these other ones also look silly. We have like switches that only have one case, so again, if we wanted to do a better job, we would probably say let's make a thing that gives us a strategy and tells us which strategy we're going to use. And so if the strategy we're going to use is a switch, we'll do that. But if the strategy we're going to use is a single if with an equal sign, we'll do that. And if the strategy is like a series of comparisons and things, give us the node, the abstract syntax tree thing that we're going to generate that off of, basically. This part, for instance, looks pretty good. I think this is basically as good as what we generate might end up looking like. We might be able to combine that into 2 comparisons instead of 3. Right, but for the most part, this looks like it worked, which is good news. So we can see here the next state begins. So this is state for identifier. So that was all code, the first 483 lines there. Now the reason it's so big is because of all these cases. Now what we could do is say, let's not let it blow out the number of lines so much so that we can see our code a little better. And what we'll do instead is say, as we're going, something like this maybe. We'll do OX2 and then if I modulo 10 equals 9, whoops, if I modulo 10 equals 9, we'll output a new line character like that. If I modulo 8 equals 7, I want to get it to be not too long of a line. Let's drop it down by 1 more. Okay. Okay, so that's all good. Now what we kind of want to do is we want to say, let's optimize out the idea that we check for any transition when we're on the last transition, right? So this only comes out if, I guess it's more like this. Since we're doing all of the transition checking there, or condition checking there, what we kind of want to do is say, if the transition next is equal to 0, we'll do a different thing altogether. And that different thing that we're going to do is to print this out with no checking at all. And the reason for that is now, when we come down here to the end of the root state, let's see, state label 2. So here's our identifier state. If we get down to here, then you'll see the last thing we do is we don't do any checks. So here we're checking if the putter is, equal to this, check a flag, check if the putter is equal to this, check a different flag, different, we get different results. So this must be checking the pound character, and if we're not inside a preprocessor body, we go to the preprocessor directive parser, and otherwise we go to an operator parser to see if it's a string eyes or a concatenate operator. And here we say anything else does this no matter what, right? Same idea can be applied right here. State label 3 lives right here, and yeah, so the last case here just doesn't even check itself, right? It just goes for it. Okay. All right, so that's all good. Next, we should do the action lists. So everywhere where we see this not implemented stuff, what we really want to do is print an action list. So I'm going to just say, let's Let's start by just saying we're going to have that, right? Gen action list. And so I'm going to take the transition activation actions, and I'm going to stick on the output pointer so I know where I'm outputting to. And so anywhere where I have determined, I've printed out the code that determines whether or not we're in a particular case. Finally, I'm going to print out the code that operates inside that case, right? Okay, active action list, right? So this just needs to be an iteration over the actions, and for each action we're going to switch on the action kind, and so here is our set of possible actions, and then all we have to do is implement the thing that turns that outputs some procedural code to do the behavior that that action requests the system do, right? So, if we want to set a flag, how do we do that? Set flag. I believe the set flag comes with some parameters. Yeah. So we're going to want to print out, and again, this is an example where if we had several set flags in a row, we would want to optimize that. So this is really gen slow action list. Because we're just making the basic one right now. So the slow action list looks like this. If we're trying to set a flag, we need to know the flag number, and then we're going to we're setting the flag to 1 or 0, so we need to if on that so that we can determine which operator to use. So if the action set flag dot value equals 0, then we're setting it to 0. We're going to and then we're going to use a bit not operator on, and then we need the code right there, right? So how do we get that? That's going to be a flag index thing. This is going to use an OR on the same thing right here. So now we need the flag indices. Indices equals gen get flag indices. We get the flag indices by going into the action flag number. So here's another problem. When I copy actions, I'm not necessarily going to do the right thing, just like I didn't copy pins correctly. So let's go and take a look at that. Where do I copy action list? I copy it right here. So just like I did in the opt copy condition, I'm going to need to do a loop over these actions once they come out. New action list first. Switch on the action, and if the action I'm looking at is an action set flag, then the action's flag pointer needs to get updated the same way this flag pointer gets updated. So we need to say, okay, go to the old to new table, grab the flag pointer that we get out of this action, right? Set flag dot flag. That gives us the old to new. We assert that we found something real. We table read the value, and then we set the action's set flag to the right thing. Okay. The emit rule, we determined we don't need to do a deep copy for that, because the emit rule, I guess the emit rule does have flag checks in it, which is actually going to be a problem. So we might have to take a quick break to do a deep copy of our emit rules whenever we copy an action that has an emit rule too. Let me look at the other things this do. So delim mark first, delim mark one pass last, and consume. None of these need any parameters at all. Emit takes an emit rule, so the emit rule we're going to need to do a deep copy on, and we're going to, as we're doing a deep copy on it, make sure that our Lexer check for each emit rule gets readjusted, and then our emit handlers themselves also have flag checks on them. So we have a Lexer check where its flag needs to possibly get updated, and a flag check where it needs to possibly get updated. These have the permission to be null. So that'll just have to be a separate thing we do in a minute. Okay. Set flag. Right, once we have that, the indices dot, what does a flag indices have in it? Variable index, and the indices dot flag value can fill in those things there. So now I should be able to find places where before it does a go to, it does something interesting. Here we go. So here it's transitioning to the string, and it sets that flag onto the flag, right? Here it's setting 4 on there because it's going into a PP directive, so that says, hey, we're going into the preprocessor. I should be able to find spots where every single flag in the system gets set now. So here's 10, 40, 80, good. 100, 4, 1, 2, 1, 2, 4, 20. So like 8. Does 8 never get set? 8 might get set in ways that aren't currently visible. I mean, 8's getting unset right there. And it's getting checked there. So 8 does real stuff. I just don't think we have any code that currently sets the 8 flag, but there are other ways to set flags. The Lexer check sets a flag too, so that must be one that gets set by a Lexer check. Okay. Anyway, moving forward, the set flag is good. Delim mark first, delim mark one pass last. We should implement that now. So how does that stuff need to work? The delim stuff is essentially going to be implemented as up here when we're first setting up our system with all the state that it needs. One of the things it needs is a pointer to the delim first, which is initially going to be pointed at input string, and the delim one pass last will also be pointed there. And so whenever we see this, all we have to do is move the delim first pointer to the delim, or the putter, to the putter, right? And the same thing here, one pass last. Now this setup would only work because we're doing contiguous input, so that reminds me that I should probably contiguous, I need like shorthand codes for these things, so this is contiguous flow slow action list for contiguous flow, right? Go to dest state for contiguous flow, go to state for contiguous flow, field set check for contiguous flow. So that's going to create a couple compilation errors. Let's go track those down. Just labeling what paradigm these helper functions are actually related to, so that I don't end up trying to use them when we go to write other paradigms of output later. There we go. Alright, so that's the delimiters. Now consume is a pretty vital concept. Consume increments our putter by 1, and that's it. Emit is the most complicated one, and we're going to have to do some extra work to even get ourselves ready to do that one. Emits come with emit rules. Emit rules themselves have conditions and handlers, and it's a list of operations that needs to get done. So emits are a little bit expensive, or can be at least. Cheap emit is possible as well if we do our job right. But we need to do a deep copy on the emits that I didn't do initially because I didn't think of the flag fix-up as an issue, which it is. So we need to do a deep copy on emits before we do anything else with emits. So I'm going to skip that and make sure that everything else looks kind of good. So here we can start to see, you know what, I will do one other thing, which is I'm going to just say throw in a comment that shows me where the emits are happening at least. So now we can see, like, alright, if I see an end of file pointer or an end of file situation, I increment putter 1 here and I emit. So this is a question I had before of, do I actually want to increment when I'm already past one pass last? Am I going to have the one pass last token, the end of file token, have a width to it that's a width of 1 at a location you can't ever reach? Maybe I will, I don't know. But that's the way it falls out of the system right now, is that that's what happens. Here, if I see a character that begins an identifier, I just consume it and I skip ahead. Here, if I see a character that begins an identifier, I consume it and skip ahead. If I look for like anywhere where I begin an operator, we'll see that I consume it. It used to be that this would have been a peak, but our high-level optimizations turned all of these into directly going to an op stage. So now whenever we see a character that begins an operator, we just consume it and go straight into the appropriate op stage, right? So 49, 50, 51, 53, 54, 56, 57, 58, 59, 60, 61. All of these are different operator stages. We have here, why would I actually have something that goes back to root from root? And what does 7b even mean? Not sure what that is. So, let me take a look. Alright, who here transitions back to root? So Lex error is the fallback here. I suppose it's possible that these have fallen out of an optimization that I'm not wrapping my head around right now. But like, what's the character 28? I need to look up the hexadecimal value of 28 and figure out why it would loop back around to root real quick. .28 is 40, open parenthesis. Aha! So these are operators that just happen to have been completely optimized down to a single consume back to root. So like 2.8 was the one I was looking at here. 2.8 is an open parenthesis. So I guess it's what's happening is it's saying I saw an open parenthesis, and whenever I see an open parenthesis, what I do is I consume it, I emit a token for it, and I go right back to root, because it turns out that we've managed to optimize out both the op stage for it and the op root that led to it. So we're skipping over 2 states and going straight back to root. So the optimizer did a good job there. That's cool. So these must all be tokens that are only 1 wide, like that have no continuation. So like, I guess open parenthesis, open square bracket, close, open brace, and all the closes. So there's 6 of them right there. Question mark doesn't have any continuations. Semicolon doesn't have any continuations. Yeah, there are a couple, and that's what it's doing with them, which is pretty cool. Comma doesn't have any continuations. Yeah. Okay, makes sense. Once it's done checking all these 1 character operators and finding them, it does a couple other checks for some other things. Z number, so this must be 0. Let's see, that would be 48. Yeah, that's right. Okay. Okay. So here's label 2. Alright, so here, right here is the fallback handler. We can see that if it sees a garbage character, so like if it sees the @ sign, for instance, which is considered a part Lexer error, it will consume that character, emit a Lexer error token, and go right back to root no matter what else happens, right? And so if all these checks fail, it'll eventually do this. Yeah, cool. So, some other thoughts that occur to me. Having these all spread out as separate switches maybe is a sort of dumb way to look at things. Maybe what we want to do is say, hey, as long as we're not sure how else to optimize things, we could just make this into one gigantic switch that covers everything from 0 to 255, and maybe then it would actually be able to do a good job of optimizing it in a way we actually like, you know? So that might be worth looking into, is seeing if we just want to merge that into one giant switch rather than having each switch be a single like bunch of cases to one handler. Right? It would make a lot of sense, actually. Yeah, okay. Let's actually just do that, because that's not going to be very difficult, and it's going to make a little bit more sense. So instead of doing a switch for every condition node, we're saying for all condition nodes, even for this guy here, so basically for all possible transitions, we're going to switch on the oops, that was too far down. Where was the so this matches this. Did I not actually have a close brace for that switch? That's kind of bad. I think I didn't. Well, now I will. So we switch on the input, and then for each possible thing, I'm going to do the following. We're going to put in all that. We're going to put in an extra brace right here to separate things out, and close brace there. And then the next case will come in after that, and the next case will come in after that. This here just needs to say that it's a default. Right? And then it doesn't need to do anything else. I guess the only thing this doesn't handle is if there were cases that oh, right. If there are any cases that have the same input but different conditions for the flags, this wouldn't work. Right? So for instance, this won't work when we're down here and we have two different things that want... Oh, those are not the same. There was somewhere in here that there's like backslash. I should look up by character what I'm looking for. So I think 92 has it. 92 in hex. This is a really bad ASCII table. It doesn't have hex. Okay. I think backslash 5C might show you what I'm talking about. No, backslash doesn't have it. Maybe pound is a good example. 23. Yeah, here we go. So you'll see that we actually have two different conditions that are both 23s. So for this to actually work, what would have to happen is any condition that catches 23 goes in the 23 handler, right? And then we have like the flag do it like an if-else breakdown, which is a little bit more tricky to organize things around, especially if things start getting really intricate. We'd have to do some fairly heavy computations to get there. No, okay, I'm going to just leave it the way it was for now, just because correcting for that is actually going to be a lot of work. Essentially what we have to do is take a set of transitions and modify its structure. Right now we just have a list of transitions, and one way or another to optimize the checking for all of them, we need to convert them into a different data structure that we can print off of more easily, because printing right off the list is going to be kind of a headache. We're going to want to think about the structure of the output we intend to create and then do a conversion and then print off of the structure that's more directly analogous to the output scheme we're going for, right? For now, we're going to do this. Okay, we'll just fix that brace mistake that I had before, and then we're good. So we're doing each of these checks separately, as we were before. Yeah. Once we have the ability to smoosh this all into one switch, I think it'll actually be, that'll probably be the way we want to do it, now that I'm thinking about it more. I mean, there's still an argument to be made that maybe we want to do like range checks on a few things, but really just a switch on 255 things, the compiler should be able to do a pretty good job at that, because that's 0 through 255, no gaps. That's all it has to handle. Yeah. Okay, how am I doing on time here? Alright, we still have 15 minutes to keep making progress. So when I print out actions, we see all these things. I want to see like the delimiter stuff. So delim first and one pass last get set right there and right there, so I can see them getting set here, they're getting set to there, so my delimiter is initially right there. And my putter, the other thing I do need that I don't have before I do anything else that I might as well just do, is I need sort of like the emit putter or something, which will start right there. And then every time we do an emit, one of the things that it does is it moves the emit putter up to the putter, and the new token it creates is the token that starts at emit putter and spans the range from emit putter to putter, basically. Okay, let's go deal with the emit stuff, and then we'll have it finished the day. So, or finished an episode at least. Maybe I'll do another one today. So when I do the copy on the action list, copy action list, it's got to be happening in here somewhere near copy model. There it is. Okay, so here I'm copying an action list, and I'm iterating the list to fix up its set flags. I also want to iterate the list to fix up its emit rules. So if the action kind is an emit, then I basically need to do make a new emit rule that we deep copy off of the previous emit rule, and when we do the deep copy, I'll pass in the old to new table so that it can do the fix up as well. So this needs to become action emit rule equals opt copy emit rule, and just like the condition copy, you're going to get the old to new. Yeah. Okay, now just a deep copy and emit rule. We're going to need an arena and an emit rule and a table of U64 that goes old to new. We're going to need a new emit to return. The new emit is going to need to be just directly copied off of the existing emit, and then I need to fix up a couple of things. So the new emit's flag is wrong if it has one. So if the new emit Lexer Check .flag does not equal 0, then the new emit Lexer Check .flag equals, I'm going to do opt flag fix up, and I'm just going to pass that the old to new table and the old flag pointer, and let that be a whole fix up routine. That way we can stop duplicating this concept everywhere. So this just returns this. Old flag goes in there. Old to new goes in there. Okay. So then all this has to do is pin flag equals opt flag fix up on the pin flag old to new, right? So there we go. That's doing a fix up. That's doing a fix up, and then later on we were doing a fix up as well. Yeah. So the action set flag is just the fix up of itself. There we go. Now, when I copy an emit rule, I fix up the Lexer Check flag, and you know what? I can get rid of this if in a couple of locations if I do this like this, right? So if the old flag does not already equal 0, we look it up, we read it, and we put it in the val, and then we do that. So probably slightly nicer to do this. Right? Okay. Old flag fix up, opt flag fix up, right? Right there we're doing the Lexer check, and then what we need to do is copy these emit handlers, do a deep copy on the emit handlers real quick. So emit handler, handler equals, take the emit's first emit handler, each of these is a handler now, and for each emit handler we're going to make a new handler by push array writing onto the arena an emit handler that's an exact copy of this handler, and then we're going to change a couple things. So the new emit handler is going to be made by, first we're going to take the new emit, and we're going to say that the new emit's first equals 0, its last equals 0, and its count equals 0. That way we can start pushing back. I guess we don't need to set the count to 0 because it's just going to end up at the same place. The new handler first, new handler, no, sorry, new emit first, new emit last, new handler, right? So that'll push that on the new handler onto the new emit, and then we just need to make sure that if the new emit has a flag check, that it gets fixed up. Everything else in there doesn't need to get fixed up. The next pointer is being fixed up by this. The kind is a copyable thing. The token name is copyable. The keywords pointer is copyable, but flag check is not copyable. So if wait, no. All we have to do is new emit flag check needs to be the opt fix up flag fix up of the original emits flag check and the old to new table. What do we got here? What are you upset with? So opt flag fix up, new emit, you want to dereference there. I get it. New emit first, last, new handler. Why don't you want to put the new handler on that? Oh, it's not a ZDLL, it's an SLLQ push. Okay, and then flag check is not a member of emit rule, so you're right. This should be on the new handler, and this should be on the original handler. There we go. Okay, so now we're doing a deep copy of our emits, so I think we can just wrap up by beginning to look at what it would be like to print out gen emit. Okay, what it would look like to do this. We might not be able to get to this today because emits are complicated, but let's just go through all the features an emit has. So, an emit rule can have, optionally it can have 1 or 0 of these. That's it. A Lexer check. A Lexer check is a chance for the state machine to set a particular flag if the lexeme it just finished parsing matches a particular lexeme that we set here. So this is basically a way to say, like, if you have a special keyword that you want to treat in a particular way, you can stick it onto your emit rule that if you see that keyword, a particular flag gets set. This is a pretty restricted rule, like concept. You can't make multiple lexeme checks, so if there are two different lexemes that should lead to two different flags, or two different lexemes that should lead to the same flag, or if you want to set two different flags from a single lexeme, none of that is possible. You can get one flag for one lexeme, or none. That's it. Those are the only things it provides. That's because it's basically hacked in there for one particular case. Now, if I wanted to generalize this system a little bit, what I would probably do is I would make the idea that this is a emit handler itself and gets stuck on there, and then emit handlers would have different flavors. There would be emit handlers that actually try to emit a token, and then emit handlers that are just a part of handling the behavior of emit in terms of like setting flags for particular purposes and stuff, right? So in that way, this is a little bit underdeveloped, but we're gonna just finish it out in this way for now, because this is what I need to get the C++ Lexer up and running. And then when I go back to look at this later and I want to make it support a few more languages, that would be a good candidate for something that I want to generalize just a little bit by making emit handler out of that, rather than having it be hard-coded. But that's what it is for now. We can potentially set this flag if this lexeme matches the code. This is like a compile time known lexeme, or rather generator runtime, right? It's known by the generator at its runtime, which happens before the compile time of the main program. And so it's going to basically write some code that says check and see if the thing we have just tried to emit, or the thing we're about to try to emit, which is a fixed lexeme that we can look at and examine, is equal to this string. If it is, then trigger this flag to be set to this value before we do anything else. Then we look at each emit handler. Each emit handler can do one of several things, a couple things basically. First of all, each one is either a direct or a keyword emit handler. If it's a direct emit handler, then it sort of is like a default. Every emit handler after it is defunct and can't possibly do anything. So what would happen is we'd see that it's a direct, and so we grab that token name and just emit out some code that sets the emit token type to be based on that token name. And using that token name, we can also look up all the other information we need: the subtoken name, flags, subflags, all of it. We also want to, during the flag check, when we go to emit, or doing the emit, when we go to emit a token, we have to do this flag check. So the flag check, whether or not it's direct or a keyword, is basically a flag that says if this flag is 0, then do not emit this. So you can't, unlike everything else in the system, it doesn't let you specify which value you're looking for. It's only the flag check for the emit handler only lets you use that emit handler if the flag you put in is set to true. So that's the only case where I hard code in the model a particular value for the flag and don't let you set it to be one or the other. That's another case of a perfectly good place where I probably want to generalize things for a more general purpose thing for generating other languages. But the quick and dirty thing that came together when I was trying to do C++ just happened to have this structure. So there's nothing else to it. If that flag check evaluates to 1, then for that particular flag, you can't have two flags in the flag check. You can't have a flag be true and a flag be false. You are only able to set one flag or no flags, and if you set one flag, you are checking if that flag is a 1. That's it. Now, there are ways to use that to get the behavior you want anyway. Essentially, you can, for instance, say do a flag check and then do another emit handler that is no flag check, and so now that emit handler only runs after the first one has failed to run. So in a way, you kind of get to say, like, okay, apply this logic if that flag check didn't work, except that you don't know if the reason the first handler didn't work was because the flag check failed or not, because there's a second kind of flag emit handler. There's the direct emit handler that just says directly emit this particular token, and then there's a keywords emit handler, and this is where we're going to have to kind of go on a tangent to get this all up and running, which is, in order to correctly emit a keywords handler, what you have to do is look at your lexeme, look it up into, hash it and look it up into a statically built hash table. That statically built hash table will tell you if the thing you are looking at is a keyword in your language or not. Or rather, it can be anything. It doesn't have to be keywords or not. It can also be preprocessor things. It can be anything that you want to check that is essentially a long thing that it's too long to do an operator parse for. So instead you are treating it as a group of things that all have the same basic lexeme structure, but then you look up into a table to find out the exact token type. And so what you can do is you look up into that table, and if that table doesn't have a fallback, then you go to the next emit handler. But tables can also have fallbacks that say, hey, if you look up into this table and you don't find the lexeme you have, then the fallback is this. So, for instance, for an identifier parse, when we're finished parsing an identifier, we will do a lexeme check, or we'll do a keyword check that'll check if that identifier is a keyword. If we find that identifier that we parsed, the lexeme that we parsed in the keyword table, then that keyword table will provide the correct lexeme or token type then. If we do not have any matches, then that keyword table also came with a fallback, and that fallback will get stuffed in there, right? So, some features we have to build out there. The other thing that happens when we emit, and it's not built into the data structure of the emit, but it's something that has to happen for each emit, is we have to do flag transport. So flag transport is the idea that we have the state machine with these flags in them. The tokens we're emitting also have flags in them, and when the system is specified, there's this idea that flags get bound. So these flag bindings get specified in the system. I think there's only one flag binding specified, and they just live right here. So this flag type has a couple of features we haven't looked at very closely, and one of them is these emit flags. And basically what that means is whenever we go to emit something, we look at all of the flags that are set, and if any of them have an emit flag, that gets transported into the tokens flags that we're emitting. Now what we can do is we don't actually have to look at all the flags. We first of all will only look at flags that actually can emit something. So it'll turn out that there's only one flag in the whole system we ever check, and it only emits one flag. So what we'll really do is we'll say, have a thing there that says, if this flag exists, then add this flag to the token as we emit it, right? And if we ever wanted to, we would have several more of them that are like, for the flags that can possibly be set, check them and emit their flags. Any flag that doesn't have anything bound for its output flag value just doesn't do anything at that point. So that will work out fairly straightforwardly, that flag emitting stuff. It's something we have to generate. So that's what we'll be doing next time, is we'll start filling in, almost there. We'll start filling in this logic to do all the different things an emit can do, which is a fairly intricate part of the system, and it's going to involve us taking a little tangent to build up the keyword generator, because right now we have the keyword lists internally stored in the model. We need to actually build make statically built hash tables out of those lists, and determine what hash function we're using for that. We probably want to have the hash function be encoded as like a 64-bit or two 32-bits or two 64-bit numbers, so that we can tweak the hash function and find one that minimizes collisions, which is something we can kind of have a little fun with. Optimizing our hash tables statically, essentially. And then once we have that, we'll be able to what's the word I'm looking for? We'll be able to build out this emit stuff more fully, but we'll need that keyword stuff first. So I think we'll do an episode of building out emit as much as we can. We'll hit up against the boundaries where we can't do stuff without the keyword system, and then we'll switch to keywords for a little while, get keywords up and running, and then switch back, get emits finished, and then we'll get back to the rest of this cogen stuff that led to all of this from there. Okay? So that's been this episode. Thanks for hanging out and checking out what I'm up to over here, and I will see you guys around later. Bye-bye.